Hi, everybody. Thank you very much for being here. This is one more session of the QRC seminar. Today we have the pleasure of having Professor Yuval Oreg. He came straight from Israel, and he's going to be here until tomorrow. Also, he has been invited by Luigi and his group and has been discussing with them. And tomorrow he will visit the lab. Professor Yuval was born in Israel and received his bachelor and master's degree in physics from the Tel Aviv University, his PhD in physics from the Weizmann Institute, and he was recruited for the Department of Condensed Matter Physics in 2000, right? Before that, he completed postdoctoral studies at the Lehman Laboratory in Harvard University. He holds the Lady Davis Professional Chair of Physics. He's the director of the Goldschlager Center for Nanophysics and an avid supporter of the Physics Olympiad team of Israel, right? So that's his trajectory. As for some awards and prizes, in 2013, he received the Michael Bruno Memorial Award given by the Israel Institute for Advanced Studies at the Hebrew University of Jerusalem. He also was the recipient of the Ser Rosa and Emilio Research Award in 2010. The 2006 Morris L. Levinson Prize in Physics, and the 2003 Friedrich Wilhelm Bessel Research Award from the Alexander von Humboldt Foundation. In 1997, he received the John F. Kennedy Prize of the Feinberg Graduate School at the Weizmann Institute, as well as a Fulbright and Rothschild Fellowship. Right? So that's a
sorry for that.
So it's really a pleasure to have you here and have the chance to hear about your work. And yeah, we will ask you questions during the
yes, please.
Yeah. Thank you very much.
Thank you for the introduction and for having me here. And please ask me questions during the talk. I have more slides of what I will succeed to tell you, so I will stop at the moment that we are out of time. But because I'm just for my first visit here, so what we see here, I will present today a study of correlated insulator and twisted bilayer graphene. I'm sure you all already heard a bit about that. So this is supposed to be, now this is theory, it's not experiment. And I will show you how we get this theory, which is more or less explain the general features that are seen in experiments. This will be the main discussion of the talk today. But before I start, I want to show you 3 trailers, so you will know, and I hope you will ask me later or tomorrow about the other thing that we are working on in my group. So one of them is, maybe you heard about Majorana fermion and topological superconductivity. And maybe you know that one of the ways to have this topological superconductivity is to take conventional superconductors in material with spin-orbit coupling and apply parallel field, which is very large. Now that appears to be problematic from the point of view that superconductors don't like magnetic fields. And what we find out is that there is a way just to manipulate the system by controlling the phases of the superconductor in a very gentle way and to bring them into a topological state. So there are several works at that direction, and it's all related. There is spin orbit coupling is involved, and actually we discussed how this different in the channel's velocity is related to the Aronov-Kasher effect. This is which is especially for you. So I hope you will ask me later on about that. So this is another work which is you know that these are a system, experimental system of quantum Hall effect. So you put this is a 2D system. You put perpendicular field which is very large, and electrons are moving, or fractional excitations are moving on the edge. Now you know that in order to study the statistics of the anyons of the excitation, usually we look on interferometers and interference between different trajectories of the anyons. Now, what we suggest here is a different way to measure the statistics, which is based, you see there is no interference here in real space, but there is an interference in the time domain. And the story is that we inject the particle here and we measure it here. And now the particle can arrive here in 3 different ways. Either it's tunnels in the first point contacts or end in the second one and arrive to here, or it's tunnel in the first one, and here there is particle Hall excitation. And the quasi-particle continue in that direction. But the electron Hall excitation can be before or after the particle that is injected here arrive to this point contact. And this before or after, when you study the interference between them, you get information about the statistics. And this is now experiment. There is a paper in Nature that was just accepted a week ago in Moti Heibel group that actually realized that type of experiment by measuring shot noise. And so again, I can tell you more about that story. So they call it time interference, and not between 2 processes in time domain. And this is really a trailer. There is a movie, as you already saw. This movie was the main thing, but I'm sorry, apologize for the time it took to start the talk. So we developed in the condensed matter group at the Weizmann Institute, we invest a lot of time in developing an online course on topological quantum matter. So there are about 20 hours of presentations with professional photographers, and this is the result. So you are welcome. Now it will be without voice. In reality, you hear voices. So that will take like 1 minute. You see. Now, notice that all are left-handed in this story. And you will understand why. Now try to think why. This is our team. So this is just a glimpse of, you can see everything online, on YouTube, on edX. Some you maybe have to register, but it's free. So you can see all the videos online, and this is how it's done. So there are, it was like really cut and all that stuff. So we really invest a lot of time in doing that, and you see why I'm writing with my right hand, but they photo it and then it's a mirror image. Okay, so now to the subject of the talk today. It was all done by my student who moved now to a postdoc in Caltech, Gal Shavi. So it's a series of papers, and there are actually more. I didn't put all of them. And please, and these are my collaborators, some of them you maybe know. And please, so it's about twisted bilayer in graphene. So basically, yeah, all the jokes are Gal, so I just took his transparencies, and there are more, which are very nice. So, but all the credit go to Gal. So we want to twist. So you know, we take 2 graphene layers, we twist them, and we get this. This is the general structure of graphene. There's a single layer. So these are the large Brillouin zone. We twist them, and we get these mini Brillouin zones of the twisted bilayer graphene. And you may have heard that there were theory, 2 theory papers, one in 2007 and the other one in 2011 by Rafi Bistacher, which, by the way, took a course. He was a PhD student at the Weizmann Institute, took a course in our department, and then move on to postdoc in the McDonald group, and they developed this idea that when you twist bilayer, you get this interesting band structure. So you get these ultra flat bands in a magic angle. Tune the system to a magic angle. So and you get these flat bands. And what we will do is we'll use a phenomenological model to describe these flat bands, and we'll see how we can explain many of the experimental features, not all of them. Now, the main thing about this model is as you change the twist angle, the gap in the system, this is the gap in the system, so it's oscillate and become extremely small in this magic angle point. Now the typical interaction parameter in the system, so it all will be about interactions. You know, when you have flat bands, the kinetic energy is very small, and the interactions is much bigger than the kinetic energy, so interaction is important. Usually in Fermi liquid theory, the Fermi energy is huge, and the interaction is much smaller than the Fermi energy. The kinetic energy is much bigger than the potential energy, so we can think about potential only as perturbation. Here, because the bands are flat, namely all the electrons have the same energy or similar energy, the interaction makes things very different. So this is why it's so interesting, and this is why people were so excited about the twisted bilayer. You get flat bands, interactions are important, just like in the quantum Hall effect, when you have Landau level, the degeneracy is very large, all the electrons have the same energy, interaction may lead to the fractional quantum Hall state. So here we expect to see also miracles and interesting stuff that happens with the interaction. Now the typical, so here there is this Moiré structure. So we see this unit cell, which is very large unit cell in real space. In the momentum space, this becomes smaller. So the typical interaction parameter is this square divided by kappa. Kappa is the dielectric constant times the distance. This distance is in the Moiré pattern. This is the typical interaction parameter, which in some cases, in the magic angle, it will be larger than the width of the band structure, which describes the kinetic energy in the system. So this is where the interesting thing will happen. So now I want to briefly tell you about the experiment, an overview of the experiment. So that was the first experiment by Carl in Pablo Yarillo Herrero group. So what they saw is that as they changed the carrier density, so what I forgot to say, and I want to say that we have two mini zones, K and K prime. We have two mini zones, and spin up and spin down. So everything is multiplied by 4. So we have like 4 flavors which are degenerate. That will be important to understand. And since we have, usually we describe them in the following way. So there are 4 bands of that type. When the chemical potential, when they are half full, we say that this is the neutrality point. This is when all the lower bands are full. This will be 0, and then we'll call it -4 in this direction and +4 in that direction. So this is the carrier density. It's similar number, but it's not, these are real number of the density. And what we see here, this is around, all the 4 bands are empty. All the 4 bands are full, and we see insulating behavior in these states. As we change the carrier density, we put more and more electrons in the system. We occupy these 4 bands. This is transport. Conductance. I don't connect anything, but Pablo Yarillo Herrero, that's I can explain. This is a graphene structure. You wrote it and you put contacts on the bottom. Yes, this is just transport, standard transport, 2-terminal transport in this. And that was the first experiment. Now they do more complicated transport measurement. But this is an example for transport. I will show different results which measure compressibility later on. But this is just transport experiment. And the basic thing is that you have regions in which the conductance is 0, insulator behavior. So this is when this is just empty band, no conductance. And this is all full band, no conductance. But you see insulating cases also near the charge neutrality point, where they're all half filled. And when 2 bands, half of the bands are full. That was the sphere experiment. And then this is called P side because the whole sides, compared to the neutrality point, this is the N side, more electrons. And what you see is as you go from 1.7 to 0.3, there are places in which this place is where you have more conductance, and here you have less conductance as you lower the temperature. So this is point towards the behavior of superconductor. You have the 2 graphene, yes. you have the two graphenes, and it's all put on a substrate which has an electrode. Initially, it was made of gold. Later on, they found out that using graphite is better because it's much cleaner, but this is the way it's done. And people know how to do devices. So this is quite, people measure conductance in graphene, so it's very similar. With the gate and so on, very similar. And usually, these graphenes are encapsulated by so-called HBN, and this HBN also have this hexagon structure, so sometimes it induces potential on the graphene itself, but this is what allows you to put insulator between the gates and your sample. So there are many details which I didn't bother to say, but no, it's good. Please, young people, ask. Okay, so this is to concentrate on that area. So what we see here is a change in the carrier density, and you really see a superconductor behavior in certain places. So what is the difference between them? This is different angle. This is 1.16, this is 1.05. So you change it by a tiny bit, the angle is completely different. Not completely, but different behavior. The details matters, the size of the domes. So people were extremely excited about the domes, and because it's reminds ITC superconductor that has also this dome structure. And what I claim is that we can understand most of the features that appears in this system. So what was interesting also is that by measuring oscillations in the magneto-resistance oscillation, one can find what is the Fermi energy. And what people found that TC over T Fermi is very large. In conventional superconductor, TC is, I don't know, few kelvins. E Fermi is 1 electron volt. The ratio between them is 10 to the -4. Here it's 1,000 times larger. So this is, wow, that is kind of a strongly correlated superconductivity. It's not something, a weak perturbation of the Fermi state. So here we are still, we don't fully understand that. We're excited about the fact that the superconducting temperature is of only 10 times smaller than the Fermi energy.
You see, the magic.
Yes.
So you would
This is perturbed a bit. What is the resistance? Here is the color code. This is the resistance. So this is a superconducting behavior. But you're absolutely right. But in the vicinity, when you measure the superconductivity here near the magic angle, you find that it's very different from conventional. What I show you, the first picture was simulation, and it's very similar. So I can discuss the temperature behavior of the resistivity. We get something which is reasonable. It's related to, here it's related to the conventional Kosterlitz-Thouless transition as a function of the temperature. We think you have vortices and anti-vortices. So.
The lower right, the lower right, if you put on your base, and then imagine what is the data.
Yes.
If I look at the right hand side, left hand side, I can see a difference in the data. What is the data on the right hand side?
I didn't put these names. No, these are names. You will see that we have an explanation for all of them.
Those are model places.
These are names. It's not. But in what we get in the simulations, if I come back to the first picture, this is again the resistance in arbitrary unit. This is a simulation, but we get regions of large resistance and regions of smaller resistance, and you will see where it comes from. No, it's a phenomenological model. I will explain. But all very good questions. Please continue to ask. I told you, I don't have to get to them. Okay, more about experiments. That's to show that they are more or less consistent, the experiment with each other. They are different in details, but some general features emerged in the system. So for example, this is a different angle, different group, different samples, different coast. This experiment was in Santa Barbara, the other experiment in MIT. But you still see near this area superconducting behavior. What they put also two gates below and above the sample. So they have displacement field. They can put electric field gate and electric field in the system. So you see there are regions. Here we see superconductivity when the resistance is very small. This is a superconducting behavior near this insulating behavior. So people say, oh, this superconductivity is somehow related to the strong correlations between the particles that lead to this insulator behavior. But you see that when they put the displacement field, it's somehow, we still have superconductivity in places where the insulator is gone. So superconductivity survives without the insulator. More experiment from Yefetov group. He was then in Barcelona. Now he moved to Munich. So you see regions in which you have superconductivity. Now there were places in which you see correlated insulator, superconductivity. So all this is another experiment, again from Yefetov group. What they did was to put a gate that screened the interaction. So that, and this is a situation in which you have more screening. So more screening give you more superconductivity and less insulator. So all these stories to say there are suggestions that the superconductivity is related to strongly correlated system, but here it seems to show that screening somehow favor more superconductivity. Interaction between the electrons, there is tunneling between the layers. This is what leads to this band structure, and interaction between the electrons in the system. In both, yes, yeah, it's even not fully screened. So the interaction are probably the same between in the layer and between the layers. They just touch each other. So this is another experiment that what they have here is a Bernal bilayer system. Bernal is without twisting at all. And the twisted bilayer here in the magic angle. So they can tune the Fermi level in the Bernal stacking to be in the metallic state or in the insulating state. So when it's, what you see is that when it's in the metallic state, TC is a bit larger. And when it's in the insulating state, you have less screening, TC is a bit smaller. Now, you know that there is this relation between TC and the gap, the tunneling gap in superconductivity. No relation at all. Delta should be, the gap should be twice, in the proper unit should be twice the TC, 1.76 times TC. Here it's 2, this is in Kelvin. So this should be 4, it's 7, there's no BCS relation. And also, here TC is smaller, but the gap is bigger. So we need something new in order to explain that behavior. So to summarize, okay, other experiments, this is not conductivity, this is compressibility. So what we saw, that's at the Weizmann Institute. So what you see here is that each time you change the occupation, you have some behavior that is repeated again and again. So you see it's something happens, then it happens again, then it happens again. So there are several features that are repeated. And the explanation that we gave them was think about these four modes which are flat. Interactions are important. And the idea now is to include interactions between the electrons. And what was important for us is that near this zero energy, there are Dirac cones. So these Dirac cones have very low density of state. So interaction is not important at the neutrality point because there are no electrons there. And as I add more and more electrons in the system, their density is increasing. And at some point, the system prefers to polarize. So if you remember Stoner instability, then the density of states times the interactions has to be equal to 1. I increase the density of state. Here it's kind of generalization. Increase the density of state. So all the 4 flavors are full. And at some point, they choose one of them to be full and the other to be empty. Then it's repeated again with 2. So this is basically the explanation for this creator, this behavior. So this was at the in group at the Weizmann. So let me summarize what we see and what we want to explain. So first of all, we see somewhat robust insulator in -2 and 2, sometimes at 3, rarely at other integer filling. Superconductivity, we see it ±2 plus epsilon, so here and there, and sometimes in the experiment weaker in this point. And is it consistent with Coulomb repulsion? We don't know. The indications are that screening helps superconductivity. Okay, this I did not explain, but I mentioned that there is this HBN, and when you align the lattice of the HBN, the insulator, with the graphene case, then superconductivity is weaker. So a theory will have to explain that. And there is this Stoner instability that reminds us Stoner-like instability, but we have more flavors, so it's more complicated. And that was somehow, we have also particle-hole asymmetry. You didn't, but we are much more insulators in the electron case than in the hole case. So a theory must explain that. HBN, hexagonal boron nitride. So this is an hexagon structure that instead of carbon in each one of them, you have boron, nitride. So this is an insulator. So the Dirac cones, because of the different masses of the 2 atoms, it's like graphene, but the Dirac cone is open, so it's an insulator. And they put it to protect the system. So in all the experiments on graphene, you will see that they get the samples encapsulated in HBN from 2 people in Japan, one car, someone else. So that is kind of what they do. And if it's a line or not, it's very important. Okay, so what we were doing, so there was a question here, we don't do, there are many people that work on that, as you know. And what we decided to do is to make a phenomenological model. So here is a model. So what we expect to get from a model at all. So this is the model, and this is the phenomenological model. So we want to do something that captures the main things, but you don't want to overdo it, because if you overdo it, you will get something which is very far from, so avoid oversimplification, and also don't expect to get everything, right? You see that there are no lips here, there's no face here. So if you want to get the details, you have to tweak your model later on. So our phenomenological model certainly will miss certain points, and we have ideas how to make it better. So for example, what I learned about that is that there is no contour line here. This is called, there are Italians here, right? This is called sfumato. Looking at the Italian that I know. So that's Leonardo da Vinci, you know, he was the only one who knew how to draw lips without it. So that kind of, just by analogy, what we should expect from a phenomenological model. I don't take all the details into account. I want to capture the main things. Okay, so what we can learn from this model. So first of all, I told you we have this 4-spin valley flavor. That will be one of the main ingredients of the phenomenological model. we insert by hand in our theory this particle hole symmetry that I mentioned. We make actually the whole band a bit wider than the electron band. But there are calculations and models that actually suggest that, but that was a parameter in our model. Now, what type of interaction we include? So first of all, we include the density-density interaction. So this lead to this idea that I fill one band, then it's push the others, spontaneously choose one of them. But which one it's choosing? That's a spontaneous symmetry breaking, like in a ferromagnet. You don't know if it's up or down. Now, we also include secondary interaction, which appear to be much smaller than the coupling between so W is the bandwidth, UC is the interaction, the density-density interaction. We have secondary interaction like exchange between the different flavors. Hund's coupling, they may prefer to be parallel in K. If I occupy K and K prime, they may prefer to be parallel. These are parameters that one can calculate. We actually took them from ab initio calculations that people did in other cases, and we tweaked them a bit. And in order to include, then this is the weakest point of our phenomenological model. We put attractive interaction on a phenomenological level. We put phonons. It could be any other glue that create attractive interaction between the electrons, but we took phonons. It could be, for example, you have spontaneous symmetry breaking. You know that you expect to have Goldstone modes. These Goldstone modes could be the glue between the electrons. We don't consider what is the origin of the interaction. We just assume that these are phonons and that they are very heavy. So retardation was important in our field. And this is the result of so basically, we get more superconductivity in the whole part compared to the electron part. We do get superconductivity in places that it does not appear in most of the experiment, probably because we didn't include this order that exists in experiment. But the general features are there. We see superconductivity in the right places. So this is a pathways of all the right. I don't know if you know this song. All the right phases in most of the right places. So that's basically the advantage of this phenomenological model. It's explained more or less what is going on in the experiment. Of course, we cannot produce all details. So now, how am I with the time? Okay. So now, from now on, if you have questions about the general structure, this is the time to ask, because now I'm going to go into details of the model itself, go deeper and deeper into the details. So, that's what I will write in a minute. Yes, of course. Of course, I will write an Hamiltonian, and what we will do, we will have parameters in the, okay. That's what I'm going to explain. Exactly what we do in this phenomenological model. It's essentially a mean field theory, which we allow certain type of orders to happen, and we just check which one is the best. Okay, so I hope it's clear what we are trying to do. So this is our basic band structure. Now, there are many ideas of how to improve that. For example, people say, oh, when you add more and more electrons that occupy the lower band, they influence the upper band, they stretch it. So there is this band renormalization. This we didn't take into consideration in our model. But this is basically the model. You ask about Hamiltonian, so this is the bands that we took. There are flavor. K up, K prime up, K down, and K prime down. And each one of them has two lattice sides, A and B, on the hexagon model. So this is our basic continuum model that describes. This is basically the Bistritzer-McDonald model. So this is the Fxk and Fyk, and we add this particle hole. So this is the band structure without the continuum model for the band structure, which has sublattice, valley, spin, valley, and sublattice. These are the three So it's 8 by 8 structure. And we have to preserve certain symmetries in the model. This is very important. So you have an SU2 symmetry. There is SU2 symmetry in each valley. And there is, I can rotate between the valleys. I can rotate the system by 180 degrees. It remains the same. These are very important symmetries of the system that our model has to preserve. So this is the basically, if you really want to know what we did, was to take that, produce this band structure. Basically, what is the origin of that? You have two Dirac cones, come from the top layer and the bottom layer, and there is tunneling between them. So what happens is that you have to draw that in more dimensions, but what happens here, that due to the tunneling between them, you get this flat band. You have avoided coset here, and you have these flat bands here. So this is basically what we do here. If Z, the distance between them, is 0, then you get two Dirac cones, right? Kx minus IKY squared. You get two Dirac cones. This is actually a structure of, yeah. Yes.
So the iron is very component, right?
8 components, yes.
Right? So what do you...
Spin, valley, and sublattice.
Okay, and what you have in between the matrices? You have
This is the matrix.
So it's 2 by 2.
Yes, you have to, it's diagonal in the spin and the valley.
So it's 8 by 8.
It's 8 by 8, but here it's, this is in the sublattice. This is in the sublattice. This Hamiltonian is in the sublattice part, and K and K prime, spin up and spin down, are equivalent, are not different. The interaction will distinguish it. But there is no spin orbit coupling in this system, so the spin is degenerate and the values are identical. So the structure here is these two Dirac cones, which are shifted. So this is in the sublattice. F of x, this one is the particle Hall. This is pH, it's the particle Hall. I didn't write it. It's something linear in K. Linear in K that actually, if you look at Bistritzer and McDonald model, they have tunneling between the layers, which does not depend on the momentum. So this is like local tunneling. The first correction to that will be linear in K, and that creates the particle. So this is like you take tunneling not only to the what is above you, but a bit to the side. So and that actually was studied in.
And then
You will see. I will. Yeah. Exactly. Precisely. Yes. It will be this, and then another one, and another one. Diagonal will be the chemical potential. Yeah. Yeah. And then we add the interaction. The diagonal is just the chemical potential, of course. Which I didn't like it. Minus mu minus t. Now, what interaction we take into account? So we take the democratic interaction, and this leads, as I told you, to this. I don't know which one of them will be full, but it's a spontaneous symmetry. And that led to this picture that explained this repeated behavior. So what are the order? So this is just changing the density, and these are totally democratic. But what we add into consideration also are the other possible order parameters. So what are the order parameters that we take, and how we did that? We take H0 and we add the interaction. So for the case of uniform interaction, this is the type of interaction that we take. And what we do is exactly what you suggest. Is we have for each, this I think spin up, spin down. This is, now I'm confused if which one is the lattice and which one is the spin. Okay. So this leads to this revival. So these are, they are all spin degenerate. And this is the difference between the different, so mu1 and mu1, this is a sublattice. And these are the four flavors, spin up and valley and spin. And as I told you, one of them we prefer to be occupied, the other no. So that leads to that behavior. Okay. So what we do is we guess that the trial state is four different four different flavors which are occupied up to mu, up to each one up to its own chemical potential. We'll just change the chemical potential until we get the minimal energy. That's the procedure. So, for example, if I'm at that filling factor, this is really the occupation. How many bands I occupy? So I put the total number of electrons. I know exactly how many particles I put in the system. I know that totally I would have 1 point something. So below 1, they are all fully equal. Yes. What I do is I calculate the energy as a function of the chemical potential and find the minimum. Yes. Yeah. And now when I know the chemical potential, I know each one. I just integrate up to the point in which precisely. So this is the filling, each one up to this one. So initially they all full together. And then at some point, one of them is totally full. This is the interaction. And the other one are a bit above the neutrality point. This is what happens here. And this is for this particular interaction parameters. Now we also allow sublattice symmetry breaking. So this is when I feel, in each unit cell I have A atom and B atom in the graphene. So if I break the symmetry between A and B, I feel more A than B, then what happens is that the Dirac cone will open a gap. So this is the sublattice symmetry breaking that we allow. Still, we only with this interaction parameter. And that means that NA is different from NB. So if we started from 2 Dirac cones, from the graphene up and the graphene down, then if I calculate the Chern number, then it jumps by 1 on each Dirac cone. That means that if I calculate the Berry integrate over the Berry curvature here, I will get just from one Dirac cone 1/2 and from the other one 1/2. So that means that we open a gap from the 2 and the Chern number jump from -1 to 1. So this is the situation here when we have this lattice symmetry breaking. So namely, if I occupied 3 bands up to this point, I will have Chern number in the system. Another state that we consider is inter-valley coherent state. So people suggest that before us, but what the story is, so you have the valley at K and at K prime. I can do particle Hall transformation for K prime, and then they form a superconductor because they have opposite spin and opposite valley. They form a superconductor. So this is called an exciton condensation state. And people, did a particular value for particular model and found initially numerically that this type of states kind of are favored. So we allow that. We add this delta inter-valley coherent state. So this is another state that we checked. And it has some symmetry properties that I don't want to discuss. This is this discussion. Just like in superconductor, when you suddenly fix the phase, here in the exciton condensate, you also fix the phase of the system. So these are the type of orders that we discussed. We also include secondary interaction. This is quite complicated. I don't want to get into details, but the main thing is to identify this parameter in the sublattice space, how these interaction parameters look. In the case of density-density interaction, it was diagonal. This O was 1, the same interaction between all flavors. Now, there are phonons in the system. There are form factor when two particles are going from K to K prime, or they on different, they go for, in K, they go in this direction, in K prime, they go in that direction. So these are called form factors. You can calculate them. They have this structure. They will influence the order in which you choose. And these are numbers that we don't know exactly, because there are screening properties. There are also disorder in the system. But we can put some typical values that are being reported in the literature that are done in these complicated calculations. So it appears that these form factors favor this coherent Kramer inter-valley coherent state. Kramer is with opposite spins. This G is due to phonons. So we include also what you see here in this phenomenological model that we take with these parameters. We clearly see difference between odd filling factor and even filling factor. They are very different. 0 and 2 are very different from 1 and 3. So this is come out due to this form factor. You know, before that, when everything was just democratic interaction, they were all equivalent. Now we add more information, and that was somehow near 2, there was a strong insulator, near 1, there was a weaker insulator. You can add also phonons. I don't want to dwell too much on that. Again, came from a McDonald group. You have to, the important thing is, and this was quite difficult because you have to identify, and in different papers, it's written in a different basis. So you know, the question, if you put sigma first and tau, then the structure will be different. So you have to be very careful about not to make mistakes in the, yeah, there was a question there? No. About what is this operator O that we have for the interaction parameters. Okay, they have different effects and different when you include these parameters. And the important thing is that these kinds prefer not ferromagnetic, but antiferromagnetic interaction between K and K prime. Now again, these are details. That's the main message, because there were questions, do I see at nu equal to 2, when I have K and K prime, do I see ferromagnet or antiferromagnet? So we say, these models say that if these parameters are large, then this is the behavior. Okay, I hope I explain what is, yeah, okay, at least the jokes are working partly, but they are not mine. So I hope you understand what is included in the model, and I gave you some hints of the details of what we put in the model. So what is the phase length? So for example, we could put some typical number. This is the chemical potential. This is charge neutrality point. And what we see here is that initially we start to feel, so let's concentrate, for example, here, what we see. So here we have one flavor, for example, K prime up, which is full, and the other one open these gaps in the system. So this is, two of them form this Kramer inter-valley coherent state with a gap. And this one is gapped as well, and this one is full. So what you see here is that this type of system will have a Chern number, right? This one has a Chern number, which is -1. And indeed, people saw that when the filling factor is 1, there is also anomalous quantum Hall effect and even quantized in certain situations. So this is consistent. Our model is consistent with that. Now, yeah, this is just what I said, that indeed people see this anomalous Hall effect, and even in certain limit, even quantized. What I want to explain now, let's examine what happened here. This is an insulator, -2. These two are totally full, and this one forms this coherent inter-valley coherent state with a gap in the system. If I go in this direction, then I start to fill up a bit, this K up and K prime down. And this is -2 plus epsilon. This is the situation here. I have two bands which are a bit filled. On the other side, I have this coherent IBC state, which is full of holes. Completely different behavior than the other side. So now it's time to introduce, when we understand 5 minutes, when we understand the main features of the diagram, I want to add superconductivity into the system. For that, I told you, we put by hand phonons, it could be any other behavior. So we add phonons. So since I have only 5 minutes, let me tell you about the phonons, and then I will go to the end of the story.
We can make like 5 minutes to wrap up, and then some people that have to go can go. But
okay.
I guess that there are more interested people that can
I have
stay,
many
right?
more slides. I will stop when the time is over.
I just need to liberate the ones that
exactly. Yeah, you are you're welcome to leave if you want. So this is the phonons. What is special about the phonons here is that you have to, usually we have one branch of phonon. And here you have to wrap up because you fold everything to the small Brillouin zone. You have to fold also the phonons. So there are many phonons in the system, unlike the one phonon that we see in conventional system. They are all fold up back, and we have to take this into consideration. So we treat that. Everything was mean field. This part we didn't do by mean field. We integrate out progressively using a renormalization group, the effect of phonons, the effect of retardation of phonons. And so unlike the usual stuff, when you have repulsion between the electrons, then you study that by this retardation effect. You know, one electron come, move the atom, goes away, and the other one does not interact with it because this one goes away. The formal way to treat it, again, electron come, pull an atom, create locally positive potential. The atoms are, the ions are very heavy, so they create momentarily positive potential, and the electron continue to move. This positive potential attract another one. This is known as the retardation effect. This is why we have superconductivity, although electrons repel each other. The formal way to do that is study that to study that, this retardation effect with high energy, we have repulsive, and below omega dB, we have a bit of less repulsive interaction. This appears to be sufficient to have this retardation effect. You pull, you have a bit less repulsion here, and this is enough to have superconductivity. Here we had to do something different. This is formally, it's a deep problem. So we instead of having one phonon, we have more and more phonons, and therefore more and more interaction as we integrate out high energy degree of freedom. Okay, that's, without going to detail, that explains why when you put a system in parallel, in alignment with HBN, you have less superconductivity because you have less phonons essentially. The superconducting behavior is very, very different if you go to -2 plus epsilon or -2 minus epsilon. And that is the general structure that we get. Weaker Coulomb repulsion, meaning more superconductivity. You see that this is a phenomenological model. We put the parameters in the way that we want. And the system is very sensitive to these parameters. Again, the general structure is similar, but the details are we have less Coulomb interaction, we'll have less insulator. More Coulomb interaction, we have more insulator. And this is consistent with the experimental result. I just want to say that, and then we will make a break. So you remember that was this story about the strong coupling limit. That TF is, TC over TF is close to 0.1. This comes very naturally in a very natural way in our model. This is TF, it's very small. This is TF, measured from the neutrality point. So it appears to be very small compared to TC in our system because TF is extremely small. That's
How do you introduce temperature? How do you introduce?
In the model, yeah, we can introduce temperature then. When we calculate, let me show you. When we calculate the conductivity, we use a model for standard superconductors that was introduced by Halperin and Nelson in '79, I think, to include the formation of vortex-anti-vortex system. So this is how we calculate the resistance.
And like phonons, they come from interactions of electrons.
The phonons are the virtual phonons are included in our system, and then we have you see, eventually we have a mean field, and all what we have to do is what is occupied and what is unoccupied. Yes. Right. Yeah. So it's both in the mean field calculation and also in the calculation of the resistance in two places. You minimize the free energy, not the energy, the free energy. You are simply right. That was not included. We have the same phonon structure. The idea is that you start from high energy and you integrate out all the phonons up to low energy. So there are many details that you can explain. There are enough details already. Okay, our message is that what we claim is that the order parameter is such that there is no remember that we have only k up and k prime down. So it's not a singlet. Singlet will need k up, k prime down, minus the other one. Here we have only two of them. So we have a strong triplet component. Okay, let's explain other experiment. Here I come to the summary. So we have a model which is consistent with experiment. It's a very rich normal state phase diagram. And now the point is that the moral from that is that if you apply parallel field, for example, or you measure the gap, what you measure are the electron correlations. Superconductivity appears just after you resolve the correlation effect between the electrons. So there are two scales in the problem, and in order to understand them, you have to understand these two scales. So we explain the rich formal, and we get this superconductivity behavior. We get the correct filling behavior, this dome structure that was a mystery that come out very naturally from our model. We understand string effect, and we also understand non-trivial spin structure. What we do not understand, we didn't include disorder. We didn't include fluctuations effect. Besides in the calculation of superconductivity, there were some fluctuations effect. This is very important. For example, I didn't tell you, but people measure huge entropy here near this insulator. One has to explain that. We have ideas how to explain that now, but probably it's due to fluctuations around the midfield. So, okay, this is the explanation of the effect of disorder. If you have time, I can explain to you later on. Thank you.
Thank you. Thank you very much also for keeping it. It was punctual in the end. It was very, timing is great. Yeah. We've had some questions. There is time for a couple more questions, then some people may leave, and of course others can stay and discuss more with Professor. Maybe any. So maybe you have some questions, but maybe some more junior.
Okay, so I emphasize that. No, I can. So I put attractive potential at some point, but the results are very far from BCF. TF and TC are so. I put attractive interaction on top of this band structure normalization. That's what we did, and this is the result of that simple consideration. Now, it's a bit, you know, people do ab initio calculations which are much more complicated. It's a bit unfair. I put some attraction and I get superconductivity, but it seems to be phenomenologically correct. So you remember in the experiment, people measure the gap, and it was very different from TC, from the BCS relation. And our explanation is that, oh, when you want to put electron in the system, you have to put it in the right band structure. So this is what determines the gap in the system. Unlike in the BCS, where there is nothing, it is just the Fermi sea and the gap of the superconductor. Here you have to put an electron into, you know, in one of the bands and to get to apply energy which is larger than the gap. Some of the states are gaps, some of them contribute to the superconductivity. So this is what you see in the experiment. This is our explanation for that. That there are two energies, two scales, or even more than two scales here that are responsible for this behavior. So one of them is responsible for the tunneling. You know, when you apply something which is above this KIBC gap, which is not related to superconductivity, its energy is, I don't know, 10 millielectron volt, while superconductivity is less than 1 Kelvin. So you have to fight with that, not with the superconductivity. So this is very different from the standard BCS. But it's a simple picture that explains phenomenologically the experiment.
So I suggest we make a break here. We thank the speaker again for the fantastic talk, and